All right, so the recording has started, and we're going to be talking about the universal law of gravity. Hold on tight. Okay, first off, just a bit of background. There are four fundamental forces that exist in nature. All right, one of them I just briefly talked about right now, which is the electrical force. You know what? I'm going to go over with this all in detail. The first two types of forces are forces that are involved in the nucleus of an atom. Now, if you think about it, why do the nucleons in the atom stick together? Right? Because as you know, in the nucleus of an atom, it's comprised of mainly protons and maybe neutrons, and that's it. But you remember learning in grade 9 that positive charges hate other positive charges. So isn't it logical that protons will hate other protons? And they will, right? So protons will repel from other protons. But why are they sticking? Oh man, I used to have one of those toys around here. It's not with me here today. It's one of those sticky toys, you know, those little fabric things that kind of look like those seeds that are outside that stick to your clothes. And protons are kind of like that, where they have this furriness around the outside. You can think about it in your imagination as that, where if you squeeze two protons really close together, they will stick together. Yeah, those are those little toys that look like little Velcro balls. If I find it, I'll show it to you guys afterwards. And that's the strong nuclear force that bonds it together. So in other words, if you place protons close enough to each other and you squish them enough, they will stick because they have this Velcro surface around them. It's not visually there, but you can imagine it as being there. Okay. So if protons are close enough together, they will hold together. That's why the nucleus holds together. But here's the thing. When the nucleus becomes too big, well, then the protons are too far away. And as you know, Velcro only works at close distances. At faraway distances, if you're too far away, the Velcro is useless, and then the electromagnetic force will take over. The protons will hate each other and repel. All right, so the first fundamental force is a strong nuclear force that holds the nucleus together. But over time, there is this other competing force called the weak nuclear force, which may push it apart. And that helps explain how nuclear decay may occur. We'll talk more about nuclear decay in the next unit. Briefly, in the last chapter, we talked about electromagnetic force. That is the force that which causes friction to occur. So that's why friction is an electromagnetic force. Other things that are electromagnetic force are, for example, like charges repel and opposite charges attract, and North Pole loves the South Pole. They will attract, and South hates South, and they'll repel each other. All right, and that's another topic for a unit 2 down in the row. All right, so we will talk about more with regards to energy and the conservation of energy in the next unit, and the unit afterwards on electricity and magnetism. So more to come on electromagnetic force. But in this current unit, we're only really focusing on one of the four fundamental forces other than friction, which is gravity. All right, and gravity is one of the four fundamental forces, which explains why things will fall in love with each other. In fact, if we're all in the classroom together right now, I usually have this really cheesy physics punchline where I say, hey, you and you and you and you, all of you guys, believe it or not, you're all attracted to each other physically. And it is true. As long as matter has mass, it has this force called gravitational force, which causes things to want to come together. And we'll talk about that in more detail today. Now, this is a lovely picture that's posted up here. And all this is just a picture just to show you the fundamental forces and how they're all linked together. All right. So as described, there are four fundamental forces. Some of these fundamental forces, they all lead together into a big theory called the grand unified theorem. Unfortunately, one of them is missing from the picture, which is gravity. All right. So unfortunately, gravity, there is no current way to figure out how gravity is related to everything. And that is the next big prize out there. There is a Nobel Prize awarded for whoever that can connect all of these fundamental forces together. Grand unified theorem, that's already been proven. That's fine. It connects the strong, weak, and electromagnetic force together. And whoever can figure out the last one, that's called the TOE, or the theory of everything. Next Nobel Prize. Who knows? Maybe it's one of you 35 students here. We'll see. Okay, so that's all you really need to know from here. Do I need to give a bit of time for you guys to jot that down, the four fundamental forces? If you do, go ahead. I'm going to mute my camera, and I'm going to try to look for that toy. As for homework questions, we'll take it up during block 4. Okay, so I found the toy already. It's this crazy looking Velcro toy. Some of you guys might have had this as a kid. All right, and you can imagine these as the protons, where if they're far away from enough, you can see that, hey, they hate each other. Look at these protons, they hate each other, they're not sticking. But if you push them close enough together, boom, they will stick together. All right, and the strong nuclear force allows protons and neutrons to bond in such manner. All right, and again, if the nucleus is too big, then unfortunately they may end up breaking apart, and that explains the instability of large nucleuses. All right, so when you talk about nuclear fission, when you talk about nuclear fission, that's when a very large nucleus snaps apart. All right, and we will cover that concept in the next unit. Okay, so I hope that's enough time for you to jot down these 4 basic concepts over here, and yeah, they will just show up as multiple choice questions. Theory of everything. All right, so that's the Nobel Prize. If you can combine the gravitational force with the other 3 fundamental forces, and you explain it through a mathematical formula or theory, probably the formula more likely, then yes, that's the next Nobel Prize. Okay, so this is a statement from Sir Isaac Newton. Okay, during, I guess, the last few years of his life. He said this: there is an inherent attraction between all objects or particles with mass. This force is proportional to the product of the 2 masses and inversely proportional to the square of the separation between the center of mass of the 2 objects. Sir Isaac Newton, quote unquote. All right, something that he wrote down in one of his journal entries, and they found it, and that was it. Done deal. All right, so he passed on, and unfortunately that didn't come to light for around another 100 years. No, not 100 years, for a few more decades, all right? Because somebody else found the research of Sir Isaac Newton and then deciphered the missing piece of this puzzle. So let's go and read this right now and create a generic equation, and I'll tell you what piece was missing. Sir Isaac Newton said that there's an inherent force attracting all objects together. This force is proportional to the mass of the 2 objects. So mass number 1, which is you or me, and mass number 2, which is good old Mother Earth. And it is inversely proportional to the separation of the distances squared between the 2 physical objects. That's what he proposed. Today, we know that there is a constant, okay? And we call that constant the big G. Kind of like Avogadro's constant, if you've taken chemistry already, 6.022 times 10 to the 23. Capital G is something. What is it? I have to cheat and look it up. 6.67? Yeah, 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. Again, the text in blue you don't need to copy down, but the text in black you do want to. All right. So again, as you're jotting this down, I'll just keep continuing on with the narrative of this. Again, Newton, he was able to conclude quite positively with regards to this correlation in his experiments. Unfortunately, at his time, he didn't know the value of G. He knew it was very tiny. He knew it was a value that was 0.000000 something, 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 but he didn't know what those values were. All right, and unfortunately, he passed on. And then a few decades later, another gentleman named Henry Cavendish, he figured out that missing piece of the puzzle. Through an ingenious experimental setup, he was able to reverse engineer and find out the value of G. Now, the value of G, this is a constant. It will be given to you for any quiz, test, or exam, so you don't have to memorize it. And if you decided to spend the $5 extra on that scientific calculator, as I said, it's worth every single penny. If you look on the back, you'll see there's a bunch of notation on the back. In fact, the first few will tell you the mass of a proton, mass of a neutron, and mass of an electron. As you scroll down looking at the text over there, there should be a capital G around. I think mine is, thought I see it, saw it, number 36. So on my calculator, I hit Shift constant 36. And once you hit that, you should be able to see the big number. Constant 36. Oh, that's not it. 39. Sorry, I looked at the wrong one. Constant 39. And the moment I type in 39, you'll see that there's a big G. What is big G equal to? Once I hit equal, there you go. 6.673 times 10 to the negative 11. All right. So that's the benefit of purchasing the calculator that is $5 more. It does a lot of extra things, including memorizing a lot of extra constants for you above and beyond just pi. Oh, this one can even do kilometers per hour into meters per second. Wow, loaded, worth $5 extra. Any questions so far before I move on? Where is const? It only exists if you paid $5 extra. Again, you have to have the higher end series of your calculators, whether if it's Casio, Sharp, or any other brands. Again, with Casio, because of its consistent nomenclature, as long as yours says FX-991, bunch of letters afterwards for a revision number, then that's the one that has the constant button. Okay, and if you have the 300 series, unfortunately, it does not include it. Yeah, the irony of it all is that that part over there with that extra features, it didn't cost them any extra to make, but they had to create a differential market. Just like with regards to most vehicles, like as you know with Tesla, there's a difference between this Tesla with auto navigation versus this one, which does. It's $5,000 more. How do you get the upgrade? You pick up your cell phone, you download the app, and you say, yeah, I'm willing to pay the $5,000 app, and somehow it installs onto your car, and now your car is worth $5,000 more. What I'm saying is that sometimes those things are already built into the calculator. All they did was somehow fuse it so that it disabled those extra features. I think someone online found a hack to upgrade a 300 to a 991, and you can probably look that up online, where you do a number overrun, and somehow it accidentally unlocks it, so you have all those features. Fun stuff about science and technology. Okay, one more thing just to mention about is that the value of r, the r is based upon the distances of the center of the two objects. All right, so it's averaged based upon that value. So that's just something you need to keep in the back of your mind. Again, the text that's written in blue, no, it's not necessary to copy down. But let's go through this example one together. Imagine two people, and you can imagine whoever you want. Probably one of them is you and your crush. Okay, and let's start solving the problem now. 150 and 50, I just made it up. That's all. All right, so let's start solving this problem over here. The number, what, capital G? Where did I get the number capital G from? Again, this is a universal constant. Okay, this is a constant that was discovered first by Henry Cavendish, and many other scientists standardized the number afterwards. I'll reveal that story in the following slide. Not the next one, but the one after. All right, let's just make sure we can get through this calculation first. This is the same exact problem as before. Okay, what is the gravitational attraction between somebody who's 150 kilograms and 50 kilograms if they are located 200 centimeters apart? A few things to keep in mind when you state your givens. All right. Now, you could describe it as capital M and lowercase m, so capital M for the bigger object and lowercase m for the smaller object, or you could use this notation as well. M1 for 150 kilograms and M2 for the 50 kilograms. What is important is that you stick with a system called the MKS system. Meters, kilograms, seconds. All right, something that which I haven't explicitly talked about before, but we probably noticed when we were solving for physics. This is a memory aid, MKS, to remind us that whenever we measure distances, it needs to be measured in meters. All right, so your value of R should not be 200 centimeters. It should be measured in meters instead. All right, those are the standard SI units used in physics. As opposed to chemistry, where they use MGS. Right, for meters, grams, seconds. Right, in physics, we use the MKS system. Okay, so that we know so far, and yeah, we do know the value of G. That's a constant, right? Kind of like 9.81 for the force of gravity here on Earth, right? Or the acceleration due to gravity here on Earth. Sorry, that's correct. Okay, so G is equal to 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. And we're trying to solve for f of G. So f of G is equal to capital G M1 M2 over R squared. So 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. I know it's a huge mouthful. Please go through the trouble of writing all that down. We're going to multiply that by 150 kilograms and then by an additional 50 kilograms. And divided by R of 2.00 meters. Just be careful, it's not just 2 meters alone, it's 2 meters squared. That's a common mistake I see students make. They forget to square the denominator. Pull out your trusty calculator and type away. 6.67 exponent to the negative 11 times 150 times 50 divided by 2 squared. You should expect an answer that's very small, all right? Because you and a person who's beside you, yes, there is this inherent attraction between you two, but as a human being with our limited intensity of sensitivity, we won't notice that force of attraction. It's going to be a very small number. And there it is. What is it? 367. 1.2 times 10 to the 7. So 1.25 times 10 to the negative 7 newtons. It's a very weak force. Okay? Just remember that Fg of an apple is approximately equal to 1 newton. All right? So you can imagine how small that number is. It's like taking an apple and splitting it up 10 million ways and taking out that 10 millionth of an apple and putting that on your finger. That is the attraction between you and a football player. All right, almost negligible.
Could you go over how to find it again?
What, on a calculator?
Just like what you have to do to find.
Again, on a calculator, after you subbed in all the values, you type in 6.67 times 10 to the negative 11. You're going to multiply it by 150, multiply it by yet another 50.
Right, I mean like the formulas, like the formulas.
2 squared. Yep, the formula is provided right on the screen, right on top right up here. It's all available.
Okay. The letters, force of gravity, gravity, object 1 and object 2.
No, capital G is not force of gravity. This is the universal gravitational constant. Do you really need to memorize that fancy word? No, just know that capital G is a constant. It's a constant that's always at this value down here. It will be a value that's provided for you on any quiz, test, or exam.
See, I know that word is like grade 6 material, but my grade 6 teacher never taught me what that word meant.
What, universal gravitational constant? No, you've never learned that in grade 6.
No, constant.
Oh, constant. Constant means a value that never changes. That's why it's constant.
Mr. Ernie, can you go back to the previous slide? Because I didn't finish my notes, just like for a sec, so I can screenshot it. Thank you. All right, I got it. Thanks.
All right. All right, so here's the universal law of gravity, and here's a sample calculation. One extra thing just to point out is that sometimes there's a minus sign right up there. And then there's a minus sign here, and you get an answer that's a minus sign. I think in your course pack, I did write down a minus, and I put it in brackets. And it's all based upon your textbook that you have. Because some textbooks just want to point out and emphasize the fact that gravity is an attractive force. So positive would be for a repulsive force, and negative would be an attractive force. Okay, so that's how it is. Okay, and I don't really care. Just know that the force of gravity is a force of attraction, so it's probably going to be the smaller object attracted to the big object. Mind you, the answer is going to be the same, right? Because if I'm attracted to the Earth at a force of 1,000 newtons, that means that the Earth is also attracted to me by a force of 1,000 newtons as well. Okay, remember that action-reaction pair. The numbers do match up from both perspectives. And we'll revisit that again at the end of this lesson. Some people might not be getting the right answer over here. Don't forget to divide the denominator squared. So don't forget to divide by 2 squared. Okay, and don't forget 6.67 times 10 to the negative 11, not positive 11, because the only way you can get to a positive answer for the exponent is if you forgot the minus sign on top. Okay, so yeah, make sure that you have a negative 11 here. Okay, any other questions before we move on? Okay, so for grade 11, we're just going to know that the force of gravity is an attractional force. So that's why I've just dropped the minus sign. But in other textbooks, they will intentionally place a minus sign there just to remind you that this is a force of attraction, right? And that's all we understand so far in our understanding of physics, that gravity is just an attractive force. I suppose that's another Nobel Prize, if you can figure out how to invent anti-gravity, right? The opposite of a force of attraction, but is a force of repulsion based upon the mass of an object. Okay, so the next part is, how in the world did they figure out that value of G, right? How do they know that it's 6.67 times 10 to the negative 11, which is the same as 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's how small that number is. Okay, it's a very, very tiny number. So how did they figure that out? Well, it was in a time in the history of science where there were multiple experiments going on at once. All right. So there was another scientist that existed during this time, and his name was Charles, I believe, Charles Coulomb, something Coulomb. I think it's Charles. Okay, Charles Coulomb, who discovered that positive charges will repel, opposite charges will attract, and this attraction repulsion, there's a measurable force. So he created an experiment to figure out what that force of attraction or repulsion was. And he ended up creating a machine that looks like what you see on the right-hand side. Okay, so what it is are those pith balls that you saw back in grade 9, and he charged these two little pith balls down below. He also had opposing pith balls on top. Now, by the looks of this, he made sure that the larger pith balls had an opposite charge, which would cause the smaller charges to rotate towards the larger charge.
How do you charge something?
Rubbing on your hair.
Oh.
Electronegativity series, if you recall that from grade 9. There's a whole chart list of all these different materials, and each one has their own affinity with electrons. Some will like electrons more, so they'll have a stronger negative charge, and others don't even care about electrons. They have a lower electron affinity charge. Okay, yeah, it's a lookup table by these days. So by noticing that it causes the string to rotate, and rotation creates a rotational force called torque. All right, it's a grade 12 topic, and you'll cover it then. But they were able to, by reverse calculating out the torque, they figured out what the corresponding force of electric attraction was. All right, and Charles Coulomb's formula, which will be covered in grade 12, I just want you to see this in comparison, looks like this: KQQ over R squared. That looks very similar to what we're learning here in grade 11, which is FG is equal to capital G M1, M2 over R squared. So here comes Henry Cavendish, who says, hey, take a look at this experiment over here by Charles Coulomb. That looks like one that I can just borrow and redo. So in his barnyard, he created this crazy looking contraption. It's a contraption where there are two huge boulders connected to a beam suspended inside his barn. Now, one thing that is true is that these two huge boulders, they are attracted to each other. However, the little degree that they attract to each other, it's almost invisible to the human eye. All right, so it tilts by ever so little bit, but you couldn't physically measure it. So he borrowed he borrowed Charles Coulomb's lab, and he did a very similar experiment where he had the huge large boulders attract towards these smaller pieces of mass. And as they rotated towards it, he kept in mind the distances between each other and the corresponding torque. In fact, you'll notice that there's a little mechanism up here, and on the far left-hand side, there was a scale. That's how he was able to determine the force of attraction. All right, so you notice that when you placed it close together, yeah, the attraction was very strong. When you moved it far apart, the attraction was lower. If you double the mass, the relationship would double. If you half the mass, the relationship would half. And by slowly going through his experiment over and over again, he was able to isolate for this value of G. Back in his day, back about 300 years ago, this is the answer that he got: 6.75 times 10 to the negative 11. Compare that with today's accepted answer. Now, you may say that these numbers are very different, but if you use that whole percentage deviation formula, right, which is the one which you do, 6.75 minus 6.67259, and you divide it by the accepted answer of 6.67259. I know that you have the whole times 10 to the negative 11, but trust me, if you carry that all the way through, you're going to get the same answer as well. And if you go through all the math for this, you'll find out the error that Cavendish made was less than 2%. It was around a 1.2% error. And that's pretty amazing, right? He was in a barnyard doing this crazy hacked up experiment 300 years ago, and he was within 2% of the correct answer that we accept today. Okay, so yeah, he was the prehistoric Tony Stark, right? Tony Stark was able to build that whole suit in a cave. Henry Cavendish did this in his barn. Okay, so science is doable at home. You just have to be very careful and take your time doing the experiment. And through enough observational analysis, you can get pretty close to the accepted answer. Okay, now this is the more or less accepted answer today. I think they're still trying to figure out these two digits over here, plus minus a few numbers. All right, and that's what I mentioned about with regards to uncertainty. All right, most of our measurements, we're only certain to 3 or 4 significant figures. To get something certain to 6 significant figures, you got to be super careful with it. If you've listened about the news about 2 or 3 years ago, they discovered gravitational waves. And here was a problem with that machine. It's a machine that, you know, is the size of downtown Toronto. All right, because I think it's like a kilometer each way or something. It was a pretty sizable machine. And that machine would actually give false answers because there was a truck 10 kilometers away driving in the neighborhood. So the vibrations from a truck driving 10 kilometers away was enough to disturb the experimental results. And that's why when they did the experiment, they couldn't do it in one location. They had to make an exact clone of the same machine somewhere else in the world. And when they noticed that when both of them received the information of gravitational waves at the same time, that was deemed as the valid information to collect. Okay, so that's the problem about measuring such precise measurements, all right, because anything can influence their answer. For our class, we're fine with just 6.67. That's good enough, all right? 3 sig fig for the most part. We're okay with that. Okay, so now's my chance to tell you about that whole letter of G. All right, we know of G as 9.81 meters per second squared, and that's all we called it. There is a proper term for it, and it's called the gravitational field strength. So here on Earth, the gravitational field strength is roughly at 9.81 meters per second squared. All right, in fact, in many physics textbooks, they just use the number 9.8 because we're not even sure about the value of 1. In fact, to tell you the truth, I can't even guarantee that the 1 is even true here where you live. Okay, because really based upon, you know, how far away you are from the center of the Earth, as well as the mass that's underneath you, and also by the fact by those two main factors. The third factor would be centripetal acceleration. If you're near the equator, you're going to get some falsified results because your illusion as it that you're being whipped away from the surface of the Earth when you're at the equator. Again, that's just an illusion, but it will impact your results. Okay, so it's not always at 9.81, and that's why I have this brief lookup table for you guys, just for your viewing pleasure. All right, so these are many different places in Canada, and you can see that the values do fluctuate, anywhere from 9.79 to as high as 9.83 in the North Pole. Okay, but I'm quite comfortable with the number of 9.81 here in the GTA area. So that's what we'll use, 9.81 meters per second squared, or 9.81 newtons per kilogram. And yes, the value will change. In fact, as you're further away from the surface of the Earth, this value will start to go down. 9.80, 9.79, 9.78, so on and so forth. All right, but it's still roughly around 9.81, even if you're flying on an airplane. So that's why it's a fairly reasonable number to 2 significant figures. The third one is probably guesstimated. But here's the end reality, and that's why I have this infographic for you over here. Yes, it's going to look like that of a curve, but let's talk about what this curve means. This curve is a relationship between the radius of the Earth, where you're on that right now, so you're right at the radius of the Earth, and your corresponding attraction to the Earth. All right, so the average person probably has a force of attraction to the Earth of about 1,000 newtons, give or take, depending upon your size. Now, if you move away from the surface of the Earth, the gravitational pull will be a lot weaker. If you recall, the formula looks like this. Fg is equal to G mm over r squared. So as you pull further away from the surface of the Earth, your weight will decrease. Now, you might think it'll decrease by a little bit, but it drops quite significantly. If you're double away from the distance of the Earth, your value doesn't cut in half. It cuts down by 1/4 because of the r squared. How important is it for you to know this stuff? Again, this is foundational information, which may show up on the multiple choice question. All right, and as you move 3 times away from the Earth, again, your value won't drop down to 1/3. It'll drop down to 1/3 times 1/3. In other words, you'll be down to 1/9 of your original weight. And the value will just keep on decreasing, but not as much the further away you are from it. All right, so the first distance that you move away is quite significant, but towards the end, it isn't as much of an impact. This type of correlation, by the way, is called an inverse squared correlation. It's a pattern that we often see in nature and in physics, and we'll see this again in other physics units. Okay, this inverse correlation over here. Fg is proportionate to 1 over r squared. That is true. Any questions so far? Inversely proportional. Oh, sorry, inverse squared. This is an inverse squared correlation. Yes, student.
Hi, so like what's like generally what is this graph showing?
Sorry, generally what is?
What is this graph showing? Just a general statement.
What is it showing? It's showing that it's an inverse squared correlation between a person's weight and their distance away from the Earth. Remember, RE is the radius of the Earth. Okay, it's an inverse squared correlation.
Okay, so people become, so they would become lighter as they get closer?
The other way around. That's why it's inverse.
Okay.
Right? The further away you are
bad.
from the Earth, the less you weigh. At some point, you'll become weightless. All right. I'm just pointing out right now, there's a common misconception people think, and what they believe is that when you're on the International Space Station, you are weightless, as in the Earth's gravity isn't pulling down on you. One thing to point out is that the International Space Station is only 400 kilometers away from the surface of the Earth. Okay, remember that RE is 6400 km. Okay, that's the radius of the Earth. And in the International Space Station, you're only 400 kilometers a little bit further. In other words, you're 6800 kilometers away. All right. And when you look at the numbers of 64,000 versus 68,000, that's not much of a difference. All right. Yeah, it's enough for there to be an impact on your weight. It will decrease by a certain amount, probably noticeable, but you won't become weightless. One thing you got to keep in mind is that the International Space Station, the reason why it can stay at 400 kilometers above the surface of the Earth is because it's quickly going around the Earth a couple of times a day. All right. So it's moving so quickly that its artificial centrifugal force, which is the force which seems to make it want to repel from the Earth, matches up with the force of attraction. And that's why inside the International Space Station, you have this perception of weightlessness. In fact, the proper term of what they're experiencing when they are in the International Space Station is something coined as microgravity, if you recall that from grade 9 Earth and Space Science. Okay, they're experiencing microgravity, and here is the grade 11 physics, just to go back to that story. Are we going to deal with any of those calculations? Not until grade 12. What are we going to cover in grade 11? Well, let's figure out what the value of G is, because as I said, that value of G of 9.81 is only true when you're at the surface of the Earth. The moment you pull away from the surface of the Earth, the value will decrease, and the more you get closer to the center of the Earth, theoretically it increases, but by the time you get to the center of the Earth, now you're being pulled in all directions. So if you were able to survive at the center of the Earth, you will be weightless again, because your net force is equal to 0. Okay, so how do we find out the value of G? We know that G here on Earth is 9.81. On the moon, it's at 1.6. And if you're on Mars, it's at 3.6. All right. And I know that none of us here have been on the moon or on Mars or any other planet, yet we already know what the acceleration due to gravity is from that planet. So let's figure out how you derive that formula. That is part of grade 11. Okay. There's a lot of gravity. It's just it's being canceled out by your centripetal acceleration. That's why they call it microgravity, because it balances out. Some things are just an illusion at the end of the day. Okay, so to make life easier, sometimes we don't call it M1 and M2. We'll just use big M for the big object and little m, or lowercase m, for the little object, just to clean up our formula. So instead of writing it out as G is equal to M1, M2 over R squared, we'll just call it G, big dude, little dude, over R squared, because that just cleans it up. And that's what we're going to do here. Okay, FG is equal to G, big M, little m, over R squared. That's a new formula we learned just now. Earlier on, we learned this other value of Fg, which is equal to mg. Again, Fg is your weight, or the force of attraction between the two objects. So if Fg is equal for both of these equations, then what we can do is that we can equate these two equations together. If you recall, m is the mass of the little person. So you can divide the little person out. All you're left with at the end of the day is this formula here. And that's a story about how you derive this formula out. In other words, as long as you know the mass of the planet and the size of the planet, you can figure out what the gravitational pull is on the surface of that planet without ever landing there. Okay. Now, some of you guys might be wondering, well, how did we figure out the radius of the planet, and how did we figure out about the mass of the planet? It's from some of it's from intuition, and others is from known references. For one thing, you can figure out the radius of the planet. All right. Now, you may not be able to figure it out on the first night that you observe it. You'll observe it maybe a few months later as the Earth orbits around the sun, and as that planet orbits around the sun in its orbital path as well. It's going to grow in size, it's going to shrink in size, and you're going to see it from a different perspective. So by triangulation, using trigonometry, you could figure out the diameter of the planet. And if you divide the diameter by 2, you can figure out the value of its radius. Hopefully that answers your question. G is for gravitational field strength.
Can you go over this again?
Okay, and remember, this is all recorded, all right? So you can watch it again there. Okay. Again, all I'm doing over here is I'm deriving out this formula down here.
Can you type the time frame if you can see how long we've been recording?
I don't even know what time frame it is. It's 1:21 right now, and we started at 12:40 or 12:45. Okay. Pretty much just fast forward until you see this screen here with GFS written on top. Yes, other students.
I just have a question about the formula.
Okay.
So from FG equals G big M little m divided by R squared, where do we get rid of the radius?
We won't. The radius doesn't get rid of. It's still there at the end.
Okay, but in where it says 2, why is it just FG equals MG?
Oh, remember, this is a formula that we covered in the past.
Oh, okay, sorry.
Yeah, this came from if F net is equal to MA, and we're talking about the F net due to gravity, which is equal to mass, times A, and if A is always at 9.81 that we assume, why not just replace 9.81 with the letter G?
Oh, okay.
That's how that formula was created, okay?
Yeah.
So we're just using a formula that we covered a few classes ago, and we're introducing a new formula that we covered right now that was first discovered by Isaac Newton, but wasn't finalized until after his death, when they finally found out what the value of G was. Now we're going to equate those two together, and with that, we can predict the acceleration on any given planet. So as I said, you could figure out the radius of the planet by triangulation, by looking up into the stars and finding out the angle of deviation, as well as the two edges of the planet. So you can figure out the diameter of the planet. Okay. So through careful triangulation, you can find out the diameter. Now, as for mass, that's going to be a bit more challenging because you need to know what the majority of the planet is made up of. And if you know what the majority of the planet is made up of, then you can estimate its density. And if you recall in grade 9, density is equal to mass over volume. And with regards to the volume of a sphere, that's equal to 4/3 pi r cubed. So as long as you know the radius, which is the distance divided by 2, you can figure out the volume, sub it in, and figure out by rearranging for mass, mass is equal to d times v. So it is mathematically possible to predict and estimate to 2 to 3 significant figures the mass of the planet. All right, and that's how we were able to determine what the acceleration was on Mars first before even landing one of the rovers on there. All right, that way we can anticipate how it's going to land and what forces are acting on the robot. And now they even have one of those helicopters on the robot now. That's pretty trippy. Yes, another question from another student.
What did you say the first few equations were? Like, what did you say to find the what of a planet?
To find out a planet, again, it's just from here. You need to know the mass of the planet and the radius of the planet.
No, to find what of a planet? Gravity?
G. Remember that G is acceleration due to gravity.
All right.
Here it's at 9.81. So in other words, if you know the mass of the Earth and you know the radius of the Earth, you could find out that it's approximately a 9.81.
What does the capital G stand for again?
Remember that capital G is the universal gravitational constant.
Okay, thanks.
Which was slated, or not slated, which was pointed out all the way back here. Universal gravitational constant. That's all it is. Okay, so now let's go through a mathematical exercise. I'm going to do it from a very abstract perspective, but hopefully you can better appreciate numbers and why things behave the way they do on Earth afterwards because of it. Okay, so let's start off with this question over here. What is the gravitational field strength from the Earth if you're as far away as where the moon is. Okay, so Earth is here right now. There you go. North America, Europe. There you go. Okay, so here's the Earth, and we're talking about X marks the spot. The spot where the moon would be as well. Okay, that radial distance. These values I don't expect you to know. I will give them to you. All right, so we know that the distance between the Earth and the moon from its center, because remember, all these calculations are all based upon the center of any given planet. Okay, so if you're as far away as where the moon is, which is 3.84 times 10 to the 8 meters, what is the acceleration due to gravity right here? What is the value of g? Hopefully you can appreciate the value is very small, because when you're at the surface of the Earth, it's at 9.81. When you're further away, it's going to drop down to probably 4.905 over here, and then half of that again somewhere over here. So, 2.5-ish, and then 1.25-ish, and so on and so forth as you move further away. But we're asking, when you're that far away, what is the value at? All right, so we'll use our newfound formula. G is equal to capital G, mass of the big person or big object, divided by the radius squared. Capital G is at 6.67 times 10 to the negative 11 newtons times meters squared divided by kilograms squared. Mass of the Earth is approximately at 5.98 times 10 to the 24 kilograms. And the radius in this case here is 3.844 times 10 to the 8 meters. And don't forget to square it. I think that's the most common mistake people make. They forget to square the denominator. All right, so work through it, and you should expect a relatively small number. 3.844 is the radius between here all the way up to where the question mark is. This is your REM, the radius between the Earth and the moon.
You say,
sometimes in scientific notation, it's hard to interpret what's going on over here. So you know what? Let's convert this into regular notation. That's 3, 8, 4, 4, 3, 6, and 2 more. Okay, so that works out to 0.00004,384 meters. We probably understand it better in kilometers. So 384, 400 kilometers. All right, what is that distance? You buy a brand new car and you drive it to the ground. That's what 384, 400 kilometers is. Okay, so you buy a brand new car, you drive it for the next 10 to 15 years until the engine explodes. That's the distance between the Earth and the moon. Somebody's asking what happened to 6.67? It's 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. Again, it's a constant. All right, and the constant has been copied down earlier in your notes. Okay, so go ahead, take out your calculators and crunch away at it. We'll work through this together. So 6.67 times 10 to the power of negative 11. We're going to multiply it by 5.98 times 10 to the power of 24. As for the denominator, just for insurance sake, maybe you do want to put in brackets, because every calculator might give you a slightly different answer. Because what you want to do is you want 3.844 times 10 to the power of 8. You want that value squared. So if you don't include the bracket, it might accidentally square the 8 for you as opposed to squaring the whole entire answer. So it's probably a good idea to include the brackets. When you hit enter, you should expect a very small number. Not super small, but somewhere in the millimeter value. And that's what I expected. 0.0027. 0.0027 meters per second squared. Wouldn't the radius be just half? This is the radial distance. Remember, this is the radial distance from the center of the Earth to where the moon is. Well, if you rearrange this formula, it has the same meaning as 2.7 times 10 to the negative 3 meters per second squared.
Cool question.
Yes.
It's meters per second squared, because from what I can see, there is newtons times meter squared over kg squared times kg. So that's newtons times meter squared over kg. Then you cancel out meter squared, so it's newtons over kg, and that's meters over second squared.
Yeah, remember we talked about this on the first
yeah,
day?
yeah, I remember.
Yeah. A Newton per kilogram is another equivalent unit as meters per second squared. They both bear the same meaning. Why is it? Because Newton said so. Newton has already defined, and in fact, I don't think it was him, it was after him, in honor of him, 1 Newton is equal to a kilogram times a meter per second squared. So when you divide both sides by kilograms, what you end up having is a Newton per kilogram bearing the same meaning as a meter per second squared. They are equivalent units. And other weird things like this exist in physics as well, where you have 2 separate units that mean the same type of measurement. All right, but I think this is the only one you need to worry about in grade 11. Okay, so let's try to figure out what the stuff here means, what that number really means. Okay, we know it's a tiny little number, so how about I just treat it as something that more of us can better appreciate. 0.0027 has the same meaning as 2.7 millimeters per second squared. And we're trying to compare that with 9.81 meters per second squared. All right. So in other words, the gravitational field strength, or your force of attraction from that far away, is peanuts compared to where it is at Earth. And you may think, that's no big deal. That's nothing. It'll take me forever to accelerate back to the Earth again. And that's true. Okay. It'll take you a very long time. But we're talking about a comparison between you and the Earth. And remember, you're just very tiny. There's something up there in the sky that's a lot bigger than you, and it's the moon. So let's revisit this calculation, even though it may seem rather innocent. And this time around, let's compare it to what's happening in real life with regards to the moon now, okay? Because remember that the first example is, what if you're that far away? Now let's take you out of that problem and replace you with the moon, okay? So that m over here, this is for the mass of the moon. We're going to sub that into here. So 7.35 times 10 to the 22 kilograms times that mediocre number over there does give us this crazy huge number. I was going to say apples. So that's a lot of apples, right? That's 2 times 10 to the 20 apples, right? If an apple is 1 Newton, that's a lot of apples. That's a huge amount of force. And what I want you to recall from this is that for every action, there's an equal and opposite reaction. So in other words, as the Earth is grabbing onto the moon and saying, get over here, the moon is also grabbing onto the Earth and saying, hey, get over here as well, at the same exact value. And we can see that each and every day because that explains why tides occur. If you guys have ever been to the Bay of Fundy out there in the East Coast, you might notice that the tides go up and down multiple times in a given day. And that has to do with regards to the moon pulling on something on the Earth, and the things that are most easiest for it to pull on is the atmosphere and water, because both of those are fluids and they're movable. All right, and we can see the consequences of it. Now, the Bay of Fundy is rather unique compared to most other places in the world, and it has to do with the natural resonant frequency of the Bay of Fundy. It is just long enough so that the water is able to swing back and forth twice a day. So once when the moon is on top of it, and once again when the moon is not behind it or on top of it. Okay, you can imagine it this way. If you're on a swing and you ask somebody to push you, do they necessarily have to push you every single time? Right? As long as they push you at the same period as your natural swing, so it doesn't have to be every time, but it could be every second time, like so. That's every second time, I think, if I'm doing it properly. All right, you will naturally have this resonant frequency, this tendency to want to move back and forth at a known time. And that's exactly what happens at the Bay of Fundy. That's why it's going to be high tide at, let's say, 12 o'clock in the morning. 6 hours later, it'll be low tide. And at midnight, it'll be high tide yet again. All right, it's naturally matched up with the period of the moon circling around the Earth. Now, when the tides are high, does that mean that the force of the moon attracted to the Earth, it is stronger at that region? Not in total, but at that region. Remember, the moon's just orbiting around the Earth itself. All right. It's just that if you're close to the moon at that moment, the moon's going to pull more of what's closer towards it, as opposed to if you're on the far side.
I have a quick question.
Yes.
Where did we get the givens from?
That's given to you.
Okay, thank you.
Yeah, I don't expect you to know the mass of the moon. I don't expect you to know the mass of the Earth. You'll eventually memorize it by grade 12 because we'll be using that number quite frequently when we talk about celestial bodies. And the last number, yep, that'll be given to you. You're not expected to know that. Okay, there is a lookup table. In fact, in your homework tonight, there is a lookup table. Okay, so if you look on course pack page, where is that? Course pack page 39, There's a lovely lookup table for you for all the references for the mass of all the different planets and its radius. Now, radius of orbit and orbital period, you probably don't need to factor that into tonight's homework, but I've given those numbers to you for your reference and for your viewing pleasure. So what is G again? G stands for gravitational field strength. That's what we're trying to solve for. And that's what we're getting at. For tonight's homework, course pack page 39, questions 1 through 6. And I think that concludes the majority of this unit.